JCC matrices, then I think from there we can apply transposes to matrices. And like for example, if I just have, let's say, some simple undirected graph, we'll just have a collection of these vertices, and I have edges between them. Right. Let's label this A, B, and C. Right. What I can do is I can make a matrix containing adjacencies, as in determining what is connected to what. Right. So for example, I create the table as follows. So A, B, C, and then A, B, C. Right. So from A to A, I have nothing connected. Right. So I'll just do 0. So we're going to give numerical values, which is determining the number of vertices attached to that current vertex graph. So for B, we have from A to B, we have a single connection, right? And this is a very special case too. So this is undirected. So that means that whatever goes from, let's say, A to B will be symmetric. So that means when we get to the row B, then we'll have a 1 there as well. But if it were directed, for example, then it would be different. Like, for example, if we had an arrow going towards A, like for example, an arrow pointing that direction, in that case, you will have a 0 here because actually, yeah, because from here, A is not connecting to B, right? It's not going toward B, which means that edge is not considered. But since we're not doing directions, there'll be a 1 there. Okay. And now for C, we just continue this process. So from A to C, we have 1 connection. And as I mentioned, the connections here are symmetric. So from B to A, I have a connection. From B, I have nothing, right? There are cases where you could have a connection to itself, right? It looks like this. But I said this was a simple graph, so there are no cycles. These little loops you might. Okay, and now from B to C, we have connection, and we just fill it in. B to A, C to B, and right. Now we have these table values, right? So this is a matrix. I can represent it as follows: 0, 1, 1, 1, 0, 1. Okay. And this is what I have, right? This is my adjacency matrix, and this contains information on just what connects to what, right? And I do it lexicographically, as in I start from A and I end at whatever the last letter. Okay. Now the transposition itself, I don't ever remember covering transpositions in graph theory, but in linear algebra, transposition is simply just a swap of the columns and the rows. So for example, if I have the following matrix, let's say A1, 1, A1, 2, A2, 1, and A2, 2. Right. So if I'm transposing this matrix, right, let's call this matrix A, right? Do the transpose. That's right. I just denote it with A to the power of capital T. That's what transposition is. What I'm going to do is I'm just going to simply swap the columns with the rows. Follow. So A11, A12. You can imagine like you have a pivot like right here, right? Like you have like these hinges, and then you just like rotate it downwards this way. So then your A11 will remain, and your A12 will come down, right? And then you'll do the exact same thing, right? So now your A21, right, will go up this way. So you'll be doing A21 and then A22, right? So that's a transposition. Okay. And so with a larger matrix, it's like that, like what that looks like. And the reason I'm doing the numerical values here, these indices, is to make it clear as to where things go. So it makes it easier to see the swaps, because if I were doing, for example, like a larger matrix, let's say A11, A12, A3, A1, A31, okay. Okay, so a neat trick with the transpositions is that you can just leave the diagonals as is, right? So A11, A22, A33 just remain. And wherever you see these positions, right, just swap them. So A21 swaps to A12, A31 swaps to A13, and A32 swaps to A2. Right? So you're basically swapping over the diagonal, right? Because here you have your diagonal right here, right? So these values don't change, right? And you're basically mirroring it over, right? So imagine you have some mirror, and all you're doing is just swapping them, right? So we'll just do that. So we have A11, A22, A33, right? And I just swap over the diagonals. And that means A12 goes here, A1 goes here, right? And I go down to the next one. So I go A31, A3, and then A31 there. And I do the last swap here. So this would be A3 and A3. Another way to look at it is the now you have that the first index is ordered it's ordered from the second index, right? So as you can see, the first index remains fixed. You have A11, A12, A13, but if we go from the original one, we have A11, A21, A31. Right? I think it's much easier just to see it this way here with the diagonal. You're just going to be swapping over that mirror basically. Well, let's see what that looks like in action with this matrix here. Right, so do 0, 1, 1, 0, 1. Let's call this B, right? So if I'm doing a transpose on this, right? The first thing I'm going to do is I'm just going to draw a line here and make it easier for myself. So this diagonal, I will be swapping over. And as you can see, we have nothing to do here, right? Because everything's already in place. So everything is a 1, so there's no reason to do a swap. So I'm going to intentionally just switch some of these so that I can perform the operation here. Otherwise, the it won't really do much because it's just the same. All right. So for sort of business, let's make sure we have all our diagonal values filled in. 0, 0, 0. Okay. And so now I'll just swap over 5 and 1. Right, so just going over the mirror, 5, 1, and I'll do it over the next value here. Right, so the at this point I'm swapping over, so that pivot, so this will be 2, 1, and then the last pivot would be here. It'll be 1, and that's a transposition. Any questions on that? On either the adjacency matrix or the transposition operation? Is my audio all good? Any confirmation?
Yep, it sounds good.
Okay. So the next thing are tree traversals. Draw a tree. So tree is a very special type of graph. It's a for one, it's a downwards looking tree, right? It's rooted going downward, not upward and topside. But trees are attributed to recursion, attributed to different algorithms involving divide and conquer. They have a very nice structure to them. In particular, binary trees, which is one I'm actually drawing up right now. But you have a root node, right? I call that R, and you have a left and right subtree, right? And whatever you have at the end, right? These are considered leaves. Right, so those are leaves. It's not leaves. Leaves. I'm sorry. I guess leaves. Leave would be a different word. Okay. So these are also considered left and right subtrees. So every node that you have here, aside from the root node, this would be a left subtree, this would be a right subtree, left subtree, right subtree, left subtree, right subtree, right? So in this case here, it's just the leaf nodes, but you could still continue adding more nodes downward on the tree. All right, so the reason I drew a binary in particular is because we're talking about tree traversals, right? So we can structure the binary tree as follows, right? We can say that if I have, let's say, some value n, anything that goes to the left of the subtree will be less than n, right? So we say anything less than n.
Okay.
N is greater here. So we'll say some k less than n. And on the right side, we'll just say this is some value that's k greater than n, right? And we continue to structure across the tree. I guess for the sake of simplicity, we'll just assume that there's no like every vertex here is unique, as in you can't have 5 and 5. Just that we're not going to be, just that we can actually see the structure of the tree as we add more nodes across. So for example, if I were to get a list of numbers, let's do 1, 2, 4. And in order to construct a tree out of this, right? So starting from the first index here, so 1, 2, 4, right? I construct the tree as follows. This will be 1, and then to the left here, nothing is less than 1, so I'll just put it on the tree on the right side. I get a 2. Okay. And then I'll continue this down there as well, because every other value is going larger. So I get this huge tree. Right? So that's just one construction. But if I can get a different list of these numbers, let's say 4, 1, 2, and 3, or actually let's swap the 3 and 2. I'm gonna get a different structure this time. So 4 at the top, 1 on the left. Plus in it, right? Okay. On the right hand side, nothing will be larger than 4. So in this case, we're going to go to the left here. And now since 1 is the left subtree, we're going to apply the same rule. So in this case, 3 is larger than 1, so it'll go on the right. And then I go back to 4, right? And then I add 2. So 2 is going to go to the left of 4. 1 is less than 2, so 2 will go on the right hand side of 1, and 3 is larger than 2, so that means 2 would be right here. So you get the zigzag pattern. Okay. That's just the inputs of the nodes themselves. So tree traversals, there are a couple algorithms, well, more than a couple actually. You have different levels. You have different types of recursive traversals. So we'll go with the first one. It's called, we have to get DFS.
Yeah.
Right.
They're both language.
So depth first search has different types of variations to them. Okay.
Get out of
So a depth first search is you're basically going as far down as possible until you reach the end. Right? So in terms of traversing a tree in this way, for example, if I have so we will travel down each subtree here until we reach the leads. Okay. It's sort of like in this path. So it's not ordered like this, so it's not going to be red, red, red here. Not to confuse you. I just want to show like we're just going to be traveling down the tree with that first search. Okay, so this is definitely. Otherwise, it's BFS. Now, BFS will be level by level. So, I do the exact same thing again. Vector search will go level by level, meaning at each individual subtree we'll be looking at its children. This is what a depth first search versus a DFS looks like. So with DFS, we go down just one of the roots, right? We're gonna go down one of the lineages, I guess you want to call it that, like you get like family trees. The DFS though, you're going like siblings down. So for example, this is the root here, right? And these are the children here. So you have the left child and the right child. So you look at those children, and then you look at the children of the left subtree, and you can continue this process. So let's actually look at the algorithm. So for DFS, there's the main ones are in order, pre-order, and poster.
Hello. Oh, okay.
So I'll go through these three here. So we'll go with in order first.
You have a location, so when you guys get to H&M, we'll be right here with you. No, walk with you.
Tree. So I'll just do a.
Yeah, because you guys are gonna pass by.
Actually, we'll make it a binary tree as we had before. So I'll just do, let's say 6.
No, I'm not keeping.
Left I'll do
I don't think there's anything.
4
I think good company.
here. 3. 5. 2. We'll just work from this tree. Let's look at what a DFS in order looks like. So in order, what I do is I process current node I'm currently at. So let's say I have a pointer starting from the root. 6. Okay. So when I say process, I just mean you do some operation upon that node. In this case, we'll do a print operation, right? Which means we'll just print whatever whatever value is associated to it. Okay. So we start at the root. So then we print out 6. Okay. And then we travel down the left subtree. So in all of these traversals, we'll be going left to right. But you will not travel to the right until you have traveled the entire left subtree. Okay. So now our pointer is here, at 4. And then we process it. Then we print 4. Okay. Then we go down this left subtree here. And we use a root. It has no other nodes, right? So we process 3. And as you can see, as I mentioned, there's no nodes attached to it, right? No children. In that case, we travel back up to 4. We've already processed 4, so we got nothing to do there. And then we travel to the right hand side.
Everything about her.
Okay. So now both the left and right subtree of 4 have been explored. So that means we move back up to 6. And 6 has been processed before. So now what's left is the right subtree. I have 8, process 8. 8 does not have the left subtree, so then I go right to the right subtree, and I reach 10, process 10, and there's no nodes attached to it, so we're done. So it doesn't end there. You actually gone back and return back to the root. Right, but since we've already processed 8 and 6, we do nothing at that point, right? So that means this will be what your result is. It's 4, 3, 5, 8, 10. It's the in order. Okay. Now let's look at what pre-order. What's the next one? Yeah, pre-order looks like. So let me erase these arrows here. Okay. So now the pre-order works a little differently than the
And then I felt like.
So what we're going to do now, actually, I think Oh, I think I know what I did wrong. So the one I did right now is pre-order, sorry.
Yeah.
I did pre-order.
Like, nice component.
Yeah,
He's not gonna look.
sorry about that. So yeah, the one I just did was pre-order. Because we do 6. Yeah, so we process it. We process it before we travel to the left and right.
You're like a very
So
good.
what we just did was pre-order. In order will be a different approach. We'll do in order now.
Yeah.
So we'll start at 6. So for in order, um we process the current node after we've traveled to the left subtree. So once we've seen the left subtree and we travel back up, then we process it. So I'll show you how that works. So for example, I start at 6, I don't process it because I have a left subtree to explore, right? So then I explore the left subtree. Okay, and I apply the same algorithm, the same step I did before. So here I check if it has a left subtree, it does, right? Then I explore its left subtree, okay, and I reach 3. So 3 does not have a left subtree, right? It's just a single leaf node. So then I process it. And then I go back up, right? And since I already processed the left subtree of 3, which was just nothing, right? It was just null. I processed the left subtree of 4, so that means now I process 4, and then I travel to the right to apply the same rule. So here I inspect 5. I see does it have a left subtree. It does not. I process it. Okay. And then I go back up to 4. Right. 4 has been processed, and I go back up to 6. And since I've explored the entire left subtree of 6, right? I process it, so now it's 6. Right, 3, 4, 5, 6. And now I explore the right subtree of 6. Okay. Now something interesting happens here. So since 8 does not have a left subtree, I process it. Because the rule is I process the left subtree and then I process the its parent node, right? So in this case, you can imagine like there's an invisible node here, right? But there's nothing there. But by the algorithm, it checks, right? If you're writing this in code, every node is going to have a left and right pointer. So in this case, in discrete math, you don't really need to think about pointers. It's just but here, if you get to the parent node and you find it has no left child, then you process it as normal, and then you go to the right subtree. So then we'll go here. Okay, we'll process 10 because it has no left subtree, and then we go back up. And we have finished the in order. Okay. Now the post order is you have to process the you have to explore both the left and right subtrees before you can process the parent node. So let's see how that works. So we start at 6. So I won't process 6 until the very end. Right, so I start at 6. I traverse down to its left subtree. I observe 4. It has left and right pointers, so then I travel left subtree of 4. Okay. Now I'm at 3. 3 has no pointers. Okay. So here, the left and right subtrees are technically visited, right? So in this case, we do process 3. So we process 3 because it's a leaf node, but by the rule of the algorithm, we have to travel to the left and right pointers, the left and right subtrees. And after we've done that, then we process the parent. And we got back to 4, so we don't process 4 yet until we travel to the right hand side. Back up to 4, and we go down to 5. Since 5 is a leaf node, we process it, right? Okay, get nothing. And then we go back to 4, So then we found, we've actually processed both the left and right subtrees before. So now we process it. And then we go back up to 6. 6 doesn't get processed just yet because we need to travel to the right hand side. Okay. Then I travel down the right subtree. 8. 8 does not have a left child, but as a right child, travel to that child. So 10 is a weak node. We process that. Come back up to 8. So even though 8 didn't have a left child, it was still processed technically since it doesn't exist. And on the right hand side, its right subtree gets processed. It had been processed already, so that means we processed 8. Okay, and now 6, both its left and right subtrees have been processed. And that's the post order of the tree. So these are the 3 main B EFS algorithms. And the last one,
The difference between me and
EFS, so it's level order.
that's the difference.
So
That's,
we do the level order in this one.
it's not for everyone.
So
And
it's easy to
I would even say don't do it. Because it's not even that. It's you're never gonna get that satisfaction that you get from something like that. It's like okay, and you're gonna keep hoping for something. And I've studied that, and I learned a lot from it. So I'm definitely like better as a person since I went through that. Yeah, that's why if we can avoid that situation,
Okay.
great.
So the level order is quite simple. It's actually pretty intuitive. You just go level by level. So I'll just draw a line right here. To note this level, so this is level, we'll call this level 0, since we like indexing from 0 to science. And I'll call this level 1 and level 2. Okay. And I go from left to right. So in this case, this will be 6. And then I process 4 and 8. And then I go 3, 5, 10. And that's it. So that is the level order, level order traversal of this tree here. And also the DFS. Any questions on that? Suleiman, did you find any practice problems? You go over?
Yep, I think they have a whole section in the about trees. So I'm in the tree traversal, so let me just bring a few questions. Where is it? All right, here. Do you want to do a few from the textbook, or do you want to actually, if you go to, let me send you, I think you have the textbook. It's under section 11.3, tree traversal. You should have, let me share my screen and show you guys. Right here. Right, so we got a couple of tree traversal questions here. Does anyone have any particular one that they want to do?
Oh, your audio is a little robotic. You're asking which questions we should go over?
These are just the questions in the textbook, because I don't think Goldberg gives like these types of examples in his notes, unless I'm wrong.
Are there any questions any students would like to go over?
Anyone in the meeting right now, Ryan, Tanjilo, Amin, any questions that you guys want to go over in particular? Or there's another topic you want to go over, we can do that as well.
I'll be returned just a moment.
You'd like to go over orders of complexity, please. What is that? Is that like big O notation? Okay. All right, we'll do that if no one has any questions. Anyone else? Maybe 9. Okay, what's 9?
I can go over the order of complexity.
What was that, Kevin? Okay, okay, you can go over that, sure.
Sorry?
maybe 9. So what's 9 asking? 9 is asking determine an order in which a pre-order traversal visits the vertices of the given order rooted tree. Okay. So Kevin, you want to go over this? Or should I? Because the way I learned pre-order traversal, I don't like they have the algorithms here too for the pre-order traversals, but it always confuse me. So when I think we learned this
Oh,
with the rope method.
yeah. So sorry, I'll be back in 1 second. Your audio is that's great.
Sounds good. So when I learned pre-order, post-order, in-order traversals, I did it with the rope method. So let's do like this. I'll just do the pre-order, in-order, post-order traversal for all of these. Right. So the idea is, right, you start here and you go along the blue line, right? And the idea is for pre-order, let's do this, so for pre-order, whenever you go to the left side of a node, that's when you like write it down. So let's do pre-order here. So we go here, we're on the left of A, so A. We hit the left of B, left of E, right? Then K. Keep going, left of L, left of M. Keep going, we keep going. We see F here, so we got F, and then we hit the left side of G. We're just going along the blue line, and whenever we're on the left side of a node, we write it down. Then we hit N, R, S. Right, we keep going. We're on the left side of C now, so C, D, H, O, I, J, P, Q. Okay. So this is the pre-order. Any questions?
No, that's good.
Sounds good. I see comes in the chat. Nope. Right. And let's go over like in order and post order traversals. Right. In order is whenever you go underneath the node. That's when you write it down. So let's start here on the rope, we're on the rope, we're on the rope, we're under the K. And then we have E. So technically this is under the E. So we write E, L, M. And technically when we go up here, we're under the B. So you write B, F, down here. Technically this counts as under the G. So I'm gonna count it. G, R, we are under the N here, N, S, that's an S, right? S. Then we go here, we're under the A, so that's A, C, keep going. I'm gonna count this as under H. It's more obvious with binary trees, but let's do that. O, this is under D, so this is D, I, P, J, Q. Okay. And post order is whenever you go on the right side of a node, right? So we're starting here, keep going, we keep going, and then K, L, M. Can you do one with prefix expressions? Sure. M, F, keep going, R, S, right? Remember, we're always doing it on the right side, so N, and now we get G, because we're on the right side of G, and B, right? And I want you to notice one thing is always notice like where the root is. So here, the root of this whole tree, we'll do it at the end, but the root of this whole tree is A, right? So the idea of pre-order traversal is the root comes before everything in pre-order. So we see here A is the first thing. In order traversal, the root comes in the middle relatively. So we see that same thing here. And post-order, once we finish the post-order traversal, we will see that the root will come at the very end. So let's keep going. We had G, B, then we C, right? O, H, I, P, Q, J, D, and then we see here finally when we come here, we're on the right side of A. So in post order, as we expected, the A comes after everything else. Okay. Any questions? Let's do a question about prefix expressions. What is the value of each of the prefix expressions? Okay. Does anyone have any questions about this? Nope. Sounds good. All good. So for prefix expressions, I'm trying to remember what this idea is. So the idea when like you have expression trees is right, any leaf node you have has to be a constant value. You can't have like an operator in a leaf node. Right? So let's try to solve these by turning these into trees. Right? So we got minus, that's because it's prefix. Correct me if I'm wrong. Yeah, prefix. This is going to be pre-order traversal. So the root is always going to be the first value. And so it's going to be minus. Then we end up with two things. Remember, in the prefix, the left tree is always first and then the right tree. So it's going to be left tree. That's the idea. We're going to have to try and figure out what's the left tree and the right tree. Times 2, 8. Sorry. Been a while since I did these. Plus, minus. Oh, okay. Let's try like this. What the hell? Why did I forget how to do this? Minus, so this minus is at the root. It's gonna be then this one. It's gonna be root tree. So then root. Two. Left and right. As no as possible. It has to be this. 2 times 8. Divided by 3. Actually,
I think you have to do it relative to the precedence from. But minus will be at the top, but then you do times 2, and then you do on the right hand side, you would do I think a divide.
Yeah.
So it won't be minus divide. I think it'll be -3 at the end. Because subtraction has a lowest precedence. Three would look like this. Here you have a 3. since multiplication is higher precedence over division. And then here you have, well, this should be. Here we have 2. And then we do 8. 5. See my 4. So there should be an 8 here. And this should be a 4. This is 4 and this is 8. So it's relative to PEMDAS. So we'll do parentheses, exponents, multiplication, division, addition, subtraction. So subtraction takes the least precedence, as in it's at the bottom, like the ordering that you're doing. The first thing you would do is multiplication, and then it comes after multiplication comes 2, and then you have the division symbols. So that will be the next operation you apply, and then you're dividing 8 and 4. So there's another algorithm I believe you can use to make this easier. You just put the operator in. Step by step.
Prefix, infix.
You begin with the first operator, and then you check if you have any numerical values. If not, then you just keep it. In this case, you're a minus. Right. And then afterwards, you come across the multiplication. And then that'll be on the left subtree here. Because we're going to be doing leftward trees, not rightward, because you're always going to be traveling left first. All right, so the next value that comes is 2. All right. So this will be also on the left-hand side, because this is going to be multiplication by 2. Okay. Next operation is division, right? And it won't be attached to the 2, because the 2 will be itself a leaf node, right? So any numerical value will be a leaf node, so it won't make sense to have division as a right subtree. Instead, it'll be the right child of the star multiplication. So it'll come afterwards, right here. And is the next operator in line is here multiplication takes higher precedence. It comes if we're talking about PEMDAS, right? So oh, I don't need to spell it out, I'm sure PEMDAS is well known now. I'll just type it out. Oh, it disappeared. Oh, there it is. Yeah. You can see it. Whatever. But yeah, it's parentheses, exponent, multiplication, division, addition, subtraction. So here, multiplication takes higher precedence than division. So we do multiplication first and divide. Okay. And now the next 2 numbers that come in line are 8 and 4. So 8 comes before 4, so that's going to be on the left side. And on the right-hand side, I'm gonna have a 4. Okay. And all the way at the end, I have a 3. And since I need a right leaf node here, and since this is the last operation we're doing, this should be the right subtree, the right child of this. So the way this is going to look, it's going to be 2 if we're doing it in order, or if we're doing the infix notation, this would be 2 times 8 divided by 4 minus 3. So what this would look like if you were to just do it with, as you would normally write it.
Sounds good. Does anyone have any other questions about this? I was doing a bit of research on how to do these questions. I mean, Famin brought it up. Do you have any questions about this? Do you want us to go over anything? in particular. For post prefix or postfix? Profix. What's that? Postfix. Okay. So I was looking at it, and I think because like you'll learn like so all this information you'll learn in 313, like how to evaluate these types of trees. Using prefix, postfix. So with prefix, I think it goes from right to left. Postfix, I'm assuming it's gonna be left from right. Postfix options. Left to right. Yep. Let's do an example here. Basically, the idea when you go left to right is you got 5, 2, 1, minus, minus, 3, 1, 4, plus, plus, times. So you go left to right, and basically the idea is you have whenever you have two numbers followed by an operator, this operator applies to these last two numbers. So then you evaluate it, and you just it's recursively, and if you think about it in that respect. So let's do this as an example. We got 5, 2, 1, minus, minus. So we're going along. We see 2, 1, minus. This will basically mean 2 minus 1, which is 1. So then we see this shortens. This becomes 1. So 5, 1, minus 3, 1, 4, plus, plus, times. Start again. What do we get? We see this 5, 1, minus. This becomes 5 minus 1. So it's 5 minus 1 is 4. So 4, 3, 1, 4, plus, plus, times. Right? We keep going. We see this. There's a plus here. So this plus is going to apply to the two constants before it. So what do we get? We get 4, 3. This 1, 1, 4 plus is going to be 1 plus 4, which is 5 plus times. Right? What do we get? We start from the beginning again. 4, 3, 5 plus. We see there's a 3, 5 plus here. This plus applies to these 3 and a 5. So 3 plus 5 is 8. 4, 8 times. Once again, what do we see? This is going to be 4, 8. The time applies to the last two numbers. So 4 times 8, 32. Okay. If you were to like go to this in prefix, it's kind of the same thing, but you just go from right to left. Right? So if we go look at this example here, we have minus times 2 divide 8, 4, 3, right to left. 4, 3, 4, 8, divide. Kevin says the division takes precedence, so it's going to be 8 divided by 4, which is 2. So minus times 2, 2, 3. Right? We keep going right to left. We see there's a 2, 2 and a times here. So then this times applies to these two. 2 times 2 is 4. What do we get? We get 3, 4 minus. This minus applies here. 4 minus 3 is 1. Okay. Does anyone have any questions? That's how you do postfix and prefix. Postfix, you go left to right. Right? Prefix, you go right to left. And you'll, in 313, hopefully you will learn the algorithms. You basically use a stack, and you have to keep pushing and popping elements to it whenever you see an operand and a constant. But once again, I don't want to confuse you guys with the algorithm. And yeah.
That's where I can learn.
Yeah, I can learn teaches it in 313 using the stacks. Any questions? Any questions at all? Nope, no questions. Sanjula, Ryan, you guys good?
Yep.
Everyone okay? Sounds good. All right, so I think Ryan wanted to go over order of There you go. Let's see.
Order of complexity of functions, I thought.
Yes. Kevin, do you want to share your screen and go over those real quick, or do you want to like go to the examples they have here?
I can quickly go over them.
Sounds good. I'm gonna stop sharing. Go to Kevin. So we're gonna go over like I think he says order of so O of one, O of log n.
Yeah.
Right. Sounds good.
You guys can see that, right?
Yep, we see your screen.
We're looking at big O notation. Let's just omit the fact that it's just a big O. Specifically, as in not really worry about what O means. We'll just accept the fact that big O is just going to be used to represent how things grow over time. Because you have other ways of measuring complexity. You have the big theta and big omega. But what big O basically gives you, it's a worst case scenario for what your outcome. So it's annoying sometimes. But what big O does, it tells you what the worst case scenario for your algorithm's runtime is. Yeah, right. So there's a couple nuances here. For one, you'll be working with just the positive axis here, right? So this is why I just drew this quadrant. So we'll say that this is the size of input here. Okay. So let's say this is n. Size of input. Over here we have what the function does over time, right? So this is going to be O of n. So in the book's notation, I believe it's just like this strange looking O. I just drew it like this because I think in most books they use this notation. But it's just letter O and followed by N. So this is going to show you how your algorithm grows over time. So size of input versus the number of operations it takes to actually complete your algorithm. Right, so we'll say that. So operations, I guess number of operations needed to complete. No. Okay. So this is what this is basically gives. And I say worst case because as computer scientists, you want to actually gauge what the worst case is, because if you get a lower, if you get a bound at, then you know you can't get any worse. Right? So as I mentioned before, you have big omega and you have big theta. So big theta, which is literally just a big theta, is the average case. So it looks like this. So this is an average case. Big omega, it's a terrible omega, better, is your best case, as in the fastest it can be. And then, as I mentioned, you have big O, which is worst case, so the slowest it can be. Okay. So the way we're going to be quantifying the speed, I guess, the slow, or fast, is relative to the number of operations you need to complete an algorithm, right? So if something grows very fast, right? So for example, if it's something that looks like this, so if your size of input, right, at very small part, like a very small size grows incredibly fast, then your algorithm is going to grow slowly. Your algorithm is going to take a lot of operations to actually complete, right? So when you see a curve like this, oftentimes it's quadratic. So this is, we'll say, big O of n squared, right? So let's not worry about these other guys over here. So theta, omega, and O. let's just stick to O, just to show you what these growths look like, right? So this is quadratic time, right? So this one isn't horrible, right? But it's not good. So this is in cases where you are looping over two sets. So for example, if I'm doing if you've seen it in your 111 class, or maybe 211 and 212, right? So if you have like two for loops, for example, like for I to N. So this colon right here just means from I to N. That's just shorthand I'm doing. And let's say for J I to M, right? So here you're doing N times N operations here, iterations, right? It's not entirely squared, but it's still considered N squared. Because M could be N. If N was significantly less than N, this will still be considered N squared, right? It's not linear, it's not just a single line, it's multiplying two integers together, right? So in this case, we give some approximation where we're going to say this is quadratic time, but this is just an example, right? This is just showing that if I have two for loops, this is going to be N squared. Now, if you imagine if I keep on doing more for loops, right, inwards for, say, Z to some other value, let's say W. If I keep adding all of these for loops, this is going to increase the complexity of my algorithm, right? So this is going to grow very fast if I add more and more for loops, right? The number of operations needed to complete the algorithm is going to take many more operations to complete because I have to iterate so much. Okay. So that's quadratic time. Now, linear time, it's very simple. It's just a single line. So the way to interpret this is I just iterate across, let's say, a list of objects, right? Or like a list of elements. I do a linear search, for example. So from 1 to, let's say, N, right? So I want to look for K, right, within this list here, right? So I go start from 1, and I go to the next index, and I keep checking all the way until the end that I find, right? So linear growth means for the input I give, right, some amount, right, the output itself will basically take the same number of operations as the input. Right? This is a linear time. So this is actually a pretty good amount of input. So a linear growth is actually really good. And once you get into data structures and design analysis of algorithms, this will become more intuitive. But it's very important in technical interviews as well to know big O notation. In particular, just O notation, how things grow over time. Just to say it again, just whatever your input is and how that scales with your algorithm. Meaning the number of operations it takes to complete it. Right? So it's always important to place a lot of emphasis in this topic here, especially to design your own algorithm. So it's linear time. So let's just write this as O(n). Okay. Now the next one is, well, I'm not really going in order, but I guess I am sort of. So I guess we'll go down. So the next one that's below it, technically is O of square root of n, but in this case, we'll skip that one because that one's a little more difficult to interpret. It's not really obvious how you take the square root of your input and then that reflects the operations needed to complete it. So we'll just skip it. The next one's O of log n. So this one's a little tricky, but once we get into the bells and whistles of it, begins to make sense. So in computer science, we work a lot with base 2, right? Literally everywhere we go, because our computers are binary, at least classical computers. So generally, when you're looking at log, this is also going to be base 2. So this is going to be log base 2 of n, right? Because logs have bases. Okay. So in your textbook or maybe more advanced classes, you're not going to be needing to write the 2 in, but generally you will be working with log base 2. And there's cases where you'd be working with like log base 3 or 4 or 5, depending on your algorithm. But in this case, as an introductory, to the O n with just the big O notation, let's just assume that log is base 2. So how do you even get log, right? So what does it mean? Let's start from there. That means as I use, or as I give more input, let's say size n, right? So size n input, right? That's the algorithm, right? The number of operations you need to complete the algorithm, right? Grows very slow, as in it's actually really good across larger inputs. And the reason for that is, let's look at an example. Let's say I have an algorithm, right, that can take a size of input 1 billion, right? Actually, let's go with let's go with 1 billion. Why not? It's a good number. That's 10 to the 9. Okay. And that's roughly 2 to the 30. Okay. So if I were to put this into an algorithm, let's say I have a black box right here, right? And my input size is 10 to the 9, which is 1 billion, right? And let's say my algorithm completes this in O of n squared, right? This is going to be a huge number, right? Well, there's more numbers that are much bigger than this, but it's going to be 10 to the 18. It's going to be a large number. So if I were to, let's say, feed this instead to an algorithm that is that has a time complexity of log n, on the other hand, right? Feed this in. We said that this is approximately 2 to the 30, right? So this is going to be log base 2 of 10 to the 9, right? And that is approximately log base 2 of 2 to the 30, right? And then using our log rules here, right? We bring that exponent down, we multiply it by the logs. We have log, this will be 30 times log base 2 of 2, right? And this is going to cancel. It's going to be 1. Okay, so it's going to be equal to 30 times 1. And look at that. We have an algorithm that takes size 10 to the 9, so 1 billion, and then just shreds it down to just 30 operations, right? So it's fast. So log is basically one of the, I wouldn't say the best time complexity you want to aim for, but I mean, just the only better one obviously is constant time. But generally you want to aim for log time, but you're not always going to get it. Because the way you end up actually acquiring log time is you are basically cutting up your input size into smaller and smaller sections. So we call it the search space, right? So for example, going back to that linear search example, you can do that, the binary search, assuming that your elements are sorted, right? Because you can just split it in half and then search for the number in either one of the halves, and you keep doing that. So you keep splitting it in half and half, your search size ends up shrinking, and your time complexity basically benefits from that, right? Because then you're gonna have log based. So you'll cover binary search and more logarithmic uses, I guess, or uses of logs comp sci, like in 313 and 323, and possibly 331. So don't worry if you don't understand this yet, but for now, just get the fact that if you're doing log time, it just means that your input size is basically being cut somehow, right? So for large input, you're going to have very small output. So it's a very good time. All right, the next operation, the next complexity is constant time. This one's kind of boring. It's just a single line. So constant time is denoted in a whole slew of ways. So one of them is O of C, right? Where C is a constant, some real number. You might see O of, for example, 1 or O of 0. Well, I don't actually, O of 0, actually, I've only seen it once. Typically, you'll see these more often. You'll see O of C or O of 1, right? They mean the same thing. Constant time just means it takes literally just a single operation to complete, right? And some examples of that are just computing numbers, right? Just doing basic arithmetic. example, if I'm using a C++ base language here, let's say int A is 2, right? Int A, int B is 3, right? And then int C equals A plus B, right? This is an O of C operation here. It's a constant time operation. It's happening in a single go. That's it. And that is constant time. Let's see. So this is basically how it goes in order. So actually, I'll write these here again. So we have 1, and this is less than O log n, and this is less than O n, and this is less than O n squared. Okay. Now we have other ones in between as well, but they're a little more advanced. I don't think we need to go over them right now. But there's some other ones though that are still worth looking at, which come after n squared, and those are the exponential time. Okay. Or cubic time, that's a very common one. Also quite intuitive, just add another for loop, and then you have cubic time. And an example of a cubic time algorithm would be like matrix multiplication, because you have to do, you're multiplying two matrices. I have to first do row by column, and then I do that for each individual row, and it turns out to be open Q. So you can verify it yourself. So after O then Q, there's some other types of time complexity, but we'll just skip to the exponential time. So it'll just be some constant. I'll just go with 2 for this example to the end. Right, so that grows very fast. So these time complexities do appear in algorithms, your science. Typically, you don't actually get to them until 323. At least the ones that grow like this. And we have factorial time, which grows really fast. Right? It's probably the fastest growing one. And factorial. Of course, you can go crazy here, right? You can just do O of n factorial to the n factorial to the n factorial times, right? So all this is basically telling you is I have some size, right? Some input size n, and the big O notation is basically telling me if I give that size, right, to my algorithm, how many operations they're going to take to finish it. So I'll just erase this one because I just kind of put that in there. Right. I can't see the chat, but I can hear people. Sure. Suleiman, are there any questions that have been written in the chat by chance?
The only question was from Tanjila. Data structure you decide to use in a program that determines its time complexity. I think that's more like a programming question. Basically, does the data structure you use in a program determine the time complexity of the program?
Absolutely. It does. For example, binary trees, inherently it'll have a logarithmic time complexity most of the time. Because if you're, for example, ordering it like this, and I want to look for, let's say 1, right? It's not going to be on the right-hand side for sure, right? So I can just cut that out. So then I basically minimize my search space. So you can continue this with a larger binary search tree. But we'll do that next. So I'll give a toy example. So I'm not going to put any numbers. I'm just going to show what happens. So this is a data structure, right? There's no code, obviously, but in our minds, this is what it looks like. So let's say I want to look for some value k right here, right? Since my binary tree, but more specifically binary search tree, because it's ordered inherently. Since I have k on the left subtree, it's not going to be in the right subtree, right? So I don't search the right subtree. So my search space decreases, right? And then I check the left subtree, right? I look for it there. And then once I get to this node here, I can do the exact same thing I did at the root, which was check where my k is. Since k is on the right hand side, that means it must be larger than this node right here. Right? So that means k is larger than, I'll call this, let's say a, right? So k is larger than a. Right, like this, it's easier to see. So k is less than, so a is less than k, right? So that means I want to search this left subtree, and that means I cut my search space, right? And as I mentioned before, when you subtract your search space, you cut it up somehow, you're going to end up with logarithmic time, right? So this is an example of binary search using a binary search tree. So this would be an O of log n operation. Okay. And if you're doing, let's say, a search with a linked list, right? That's another data structure. A linked list is just a connection of these nodes. Same nodes, same definition of a node in terms of graphs, except now you're just doing these very rigid connections, right? You're going either left or right. So let's say this is just like a singly linked list, right? As in just it's going from one direction. If I want to look for some value, sorting this is not going to be very easy. Sorting linked lists is very difficult. Well, they're not impossible or hard. It's just it's like, it's not really attractive. But assuming that this isn't sorted, right? And you just want to search for something, I'm just going to go through each individual, right? So 1, 2, 3, 4. And I look through each individual one and see if my node, let's say I have a value associated to it, so A, B, C, D, right? And I want to look for C. I check if C is the first node. Now I go to the next one and I find it. Great, return it, right? Inherently, that operation is going to be linear. So in this case, the linked list is going to have O of n search time, right? But with a data structure like an array, for example, or rather not just search time, let's just say you want to just access something, right? So a linked list doesn't have indexes associated to each individual node. It's just it's somewhere in the memory, it's in RAM, right? With an array, for example, it's contiguous, right? You have cells associated to each individual slot here. Okay, so let's say this is some number of slots. In a linked list, I can't access the index. I have to go through each individual node. But if I wanted to access a value within my array, right? Let's say this was index k right here. And let's say in this example, I don't care about what values stored to k. I just want to know what's at k, right? All I have to do is just, let's say if this was C++, right? This would be an int array as follows, right? Let's say I added some stuff into it, right? Like some numbers 1, 2, and okay. If I want to access some value in the array, then all I will do is just say array of k, right? There you go, I access it, right? And I can assign it to something, or I can use it in some addition, anything, right? I access it. But this is an O of C operation. It's a constant time access immediately. With the linked list, on the other hand, I can't do that, right? I guess what you could do is try implementing some pointers to it, but inherently the way you're learning it, on the very first start, you're not going to have any indexes associated to the linked list. It's just going to be these connected nodes, and if you want something, you're going to have to travel through each one. So accessing values is constant time for an array, but for the linked list, it's linear time. Best case scenario, it's going to be constant time for linked list. But in the average case, you're going to have to search the whole thing. So, yeah. And there's some other data structures out there as well that I don't think have been covered yet in the classes here. I want to hold up Suleiman if he has something to say.
Nope, we're all good.
Any other questions, perchance? Are there any questions in chat?
Donjilo's asking, what about hash maps? What time complexity is hash maps?
Perfect. Yeah, great. So you guys have covered hash maps. Hash maps, that's actually a really good one. So hash maps have different implementation. So some of them use trees, specifically red black trees, which will cover in data structures. But let's say that you're not using a tree, but it's just you're just using, let's say, some sort of container. I mean, it looks like this. It's just some long hallway, and you have indexes attached to each one, just like some array. Right, and then at each index you assign it, you have some sort of hashing algorithm, means that you have a key, you have some key value pair, right? So key value pair. Okay. And let's say you have your hashing algorithm, apply it, and it assigns it some random position. It's not gonna be random, right? It will be pseudo random. So let's just not worry about the hashing algorithm, but the fact that we assigned it to some position, right? So right here, and then we give ourselves a value, right? The key is at this position, and the value is there. Right? So just like arrays, the access time is constant. Right, so accessing values within a hash map is constant time. So if I used in C++, for example, an unordered map, which is a hash map, and let's say it was integers. So this is a key, this is a value. Map. Right. If I want to input something to it, right? Let's say a map. Actually, let me just do let me do this. Let's do a chart here. This would be map, let's say, of a letter C. Actually, let me do letter A. Equals to, let me assign it to 1. Right. If I wanted to access the value of A, right, this is just going to be, you know, I'll just do C out, for example, map, and I will put in the key, right? The key is A, and I'll do an end line here, for example. Okay. And this is going to be a constant time operation, because we're simply just accessing that slot right there, right? We're using our key, we're unlocking the door, and then we have it, right? It happens instantly. So interesting thing about hash maps is they have all sorts of different types of implementation. As I mentioned before, there's a tree implementation for it. But you have different ways of probing, which you'll cover in data structures. Probing means it's related to the fact that if I have, let's say, my key, right? And my key has been generated by this hashing algorithm, right? Since I have a finite number of cells within this hallway that I have here, I'm just gonna call it a hallway since it's just like a long strip. If I were to run a hashing algorithm when I'm trying to input something into the map, and it turns out to land on the exact same spot, one of two things can happen. Either I push it to the side, right? I'll have two values associated to it, right? And it's like sort of like it's lined up, or I just replace it. Or the third case, I mean, I mentioned two, but just three actually, is you probe it to another location. Right? So you move it. So let's say it's at K, and there's something already at K. You just move it somewhere else. So we'll just say it goes to the next slot comes after, so K plus B. So now inputting elements into the hash map has changed all right now. All like outright changed, because now when you're doing this probing, right? In this case, the example I said was linear probing, which you're just simply just if it's already at a particular slot, then you just put it to the next slot. So that means now inputting elements into your map is now linear, because let's say everything else here, right, was already filled. And so let's say from 0 to 5, you had something, you had a value 1, value 3, right? And then I try putting a value in here, and then the hashing algorithm gives me the key 2. I can't put 2 there. Actually, no, let's do this. The hashing algorithm gives me the key 0, right? I can't put it at 0. I can't put it at 1. So I move to the 2, I move to 3, and I move to 4, and I put my value there. Right? So I keep on looking for that empty slot. So that's a linear time, because you're basically going through each one by one to input it. So hash maps are a little trickier when it comes to time complexity, because it depends on your implementation. But that's just a sneak peek for what you'll expect in P13. And then you have other forms of probing, like quadratic probing, which instead of just going to the next slot available, you square the value. So for example, if I'm not available at 2, then I square it, I try 4. If that doesn't work, I try 16, and I go around. Another thing is also, if 16, obviously this goes to n, so you might not have 16. In that case, you just do the mod, right? You'll do 16 mod n, and you get the remainder, and then you wrap around. That's what you will do. Just a bit of information for you guys, in case. Any other questions?
They're asking, did you say square 2, 4, and n? I think for
Oh, yeah. So what I mean square is, like, let's say 2 is not available, I square it, right? I check 4. If that's not available, then I square it again, and I get 16, right, from this, right? Now, I was mentioning that I might not have 16 available, because there might be, like, let's say 10 slots. Then in order to wrap around, so that I'm not, running into like out of bounds issues, I'll take the mod of it. I'll take the remainder. So 16 modulo n. And I keep on repeating this until I have a slot of. So I'll do like a quick example. I have 0, 1, 2, and 3. Right? Let's say I already have some stuff already available here. So let's say 1 already has something here. So let's say I try putting in a value 2 into the slot 1. Right? I square it. It's 2. And I put it in there. Okay, great. Okay. Now let's say I have another value that comes in, say v3. I try putting it into this slot. I can't. So what I do is I square that. So I get 2 squared, which is 4. Okay. Now, in this case, n is equal to, how would I do this? N is equal to 4, because you have 1, 2, 3, 4 positions. In this case, I will do 4 mod n, which is going to be 4 mod 4, which is 0, which means the value I put will be located here. That's what I do. Actually, now thinking about it, if I'm at 0, I square that, I'm still going to get 0. So let's just say that it were just it's 1, 2, 3. Put this again, because if I square 0, I'm not going to get anywhere. Wait. Did I say 1 square? That's wrong. Sorry. I think there's special cases for 1 and 0. Yeah, obviously if I square 1, I'm not gonna get 2. We have 1. So let me do that again. So let's say I was at v1, right? So 0 and 1, I think will be treated differently, because if I square 1, I'm just gonna get it again, and the same thing happens with 0. So I think what happens is I go to the next one. You can correct me if I'm wrong, so I think what happens with these cases is that you go to the next value. It's not available. For example, if I have like something here like v2, and I try going here, then I go to the next one. Otherwise, if it's not 1 or 0, then I square. All right, let's see that in action. So let's say I try putting in something in the slot. Let's say I try putting v2 in the slot. This would be 2 squared, which is 4. Right. So that means I go to this slot here, I go to slot 4. And then I put it.
I just want to point out for a case, maybe for cases like 0 and 1, like for quadratic, it could be the formula like instead of just x squared, it could be x squared plus 1, just to avoid like those
Yeah,
corner.
yeah. Correct,
Yeah,
correct.
just to avoid being stuck on perpetually 0 and 1. So it's not always x squared, it could be x squared plus 1 or any formula.
Yeah. But this was just bit of a detour. Like this is data structures now, but I
Well,
haven't
that's
answered
fine. I feel like 220, there's a lot of
It's fine.
it related to data
Yeah,
structures.
I think
And
yeah.
then, does anyone have any questions? It could be about the data structures, that's perfectly fine as well. I think for a quiz, we've gone over pretty much everything that we need to. Does anyone have any other questions they want to go over? Any other topics? Got like 25 minutes left. And for those who will be wondering, we are recording this meeting. So for any one of those of your friends who wasn't able to show up, maybe you let them know we are recording this. We got a little bit of a sneak peek to data structures. Anyone at all? All right. What was that, Kevin? Sorry.
Coming summer, just fall, stuff. Whenever you're taking data structures.
Angela, me, and Ryan. Anyone have any questions? Any other topics they want to go over?
Would you show the syllabus again?
The syllabus once more. Okay, I'm gonna share my screen. Never mind. Share screen. Syllabus. Share. All right. So I believe you mentioned 8 through 13, 8 through 12 actually. So here. And also, I think Daniel, you mentioned you're gonna go over induction next class. So even if you want to go over anything before that or anything in the past, we got time. Any topics you guys want. So
Oh, what, you meant induction or something?
no, because you said I believe you mentioned your next class is gonna go over induction.
Yeah.
So if even
Then
though
we gotta-
these topics aren't gonna be on the quiz, if you want, because we did technically go over algorithms and growth functions, any of these from before, or even before quiz 1, if anyone wants to go over any of these topics, feel free to ask. Got some time to burn.
Yo, could you send me that, like, whatever, I don't know how you got it in this form, because he sends everything in Excel. Would you mind sending me this? Like this page?
Sounds good. There you go. Okay. Anyone have any questions in particular?
Thank you. Okay.
Wonder what master theorem is. I think that's like relating to divide and conquer.
I think master theorem, it's the theorem we learned like with if it's like with log n and like a, b, c, and d, then let me see if I can pull it up. We learned Mitchell teaches it near the end. It's like with big O notation. Growth of functions.
I think it was right after like base something. I don't know.
Um, something like let me see if I can pull it up.
You guys are going over Chomsky hierarchy too.
Yeah, this
Great.
part's weird. They're going over grammars, Chomsky hierarchy, deterministic, non-deterministic.
Monster theorem, the divide, conquer, recursion.
Action pack 220 class.
It's a lot.
Mine was just graph theory and just reduction.
Yeah.
Reduction, recursion, recurrent relations. That's your theorem. I think that has to do with recurrent relations.
Well,
No,
if
yeah,
anyone
with
has
divide and conquer.
no other questions, I think we can end it here.
Yeah, sounds good. If everyone's good, I think once again, there's only so many questions you could force out of 3 students who showed up, but if everyone's good, I think this is where we might end it. Last
Yeah.
call for questions.
Yep.
Oh shoot, before you don't leave, no, don't leave yet. No, don't leave yet. Hold on, hold on, hold on, hold on, hold on. Don't leave yet. Before you leave, I'm just gonna please fill out this feedback form. Kevin did a great job today, but if you guys have any other feedback for us, I believe we're gonna be doing another one for the third quiz and also for the final. But if you guys have any feedback, please fill out that form. Even if it is just the three of you, that's gonna be very, very important. And I'm just gonna quickly share my screen to show where it's gonna be, the recording. So if you go to the website, I believe you guys here should know this by now. Go into resources, computer science resources, and we have a little section here, 220. Right now we have the review sessions for Delram and Calling Up. You should be able to see, I think hopefully by this Monday or Tuesday. I don't know when your quiz is, but hopefully by when the break ends on Monday, you will see the recording for this current review session. So if those of you here and for anyone who wasn't able to show up, you will be able to find it here. Okay. And yeah, don't forget to fill out the form, and I will stop the recording now.